Hello everyone, and thank you for joining today's webinar entitled Enhancing Switch Reluctance Machines Performance Using Permanent Magnets. My name is Ali Vakilian and I am an electrical engineer and motor design expert at EMWorks. EMWorks is a leading provider of electromagnetic simulation software for electrical and electronic designs, from DC to millimeter wave frequencies. Our products are embedded in the most popular CAD platforms, namely SolidWorks and Inventor. EMWorks products covers a wide range of applications ranging from electric motors, generators, transformers, and power electronics at low frequency to antennas and various wireless circuits and components at the high frequency. We provide four main products. Motor Wizard is a template-based motor design tool that helps to design the motors without need to CAD drawing. With defining geometry parameters, you will have initial design outputs and full CAD model for further analysis. Beside Motor Wizard, EMWorks 2D offers 2D finite element simulation environment with various analysis options like magnetostatic and transient simulation, motion coupling, thermal coupling, eccentricity simulation, and many other simulation options. EMS as a 3D simulation product can cover many applications like electromotors, insulators, cables, circuit breakers, and transformers. The last product is HFWorks, which is used for high-frequency simulations. It will cover many applications like antennas, connectors, and etc. If you need any further information, you can visit our website www.emworks.com. I request all the participants to please feel free to ask their questions using the chat box option, and we will address all the questions at the end of the presentation. Now let's have a look on today's webinar agenda. First, we will have an introduction about the switch reluctance motors or SRMs. Then we will compare switch reluctance motors with other types. Working principles of SRMs will be illustrated then, and we will discuss about modular stator of SRM. To enhance the performance of this type of machines, we will talk about PM-assisted switch reluctance motors, and we will see the simulation results. The simulations are done in finite element software, EMWorks 2D, and we will have a simulation demo, and the last parts will be conclusion and question and answer. Switch reluctance motors were invented in 1838 by W.H. Taylor, and it is patented in United States. They operate based on change in the magnetic reluctance. The rotor and the stator poles are salient and they do not have any permanent magnets. The field windings are mounted in the stator poles, and rotor doesn't have any winding or PM. Like any other kind of machines, SRMs have their own advantages and disadvantages. Simple structures, concentrated windings that helps to have easier manufacturing, simple and solid rotor part without any magnet or windings are advantages of this kind of machine. Of course, without any coils in the rotor, we won't have any loss in the rotor. So all loss happens in the stator, and cooling is much more easier than motors like induction motors. But this kind of machines has disadvantages too, like high torque ripple and acoustic noise is the main drawback of these motors usage. And to drive these motors, we need position sensors. Unlike induction motors that can be directly connected to the three-phase, we need a driver with position sensor to drive and start these motors. To have an insight on these motors, let's compare SRMs with two popular motors in the industry, induction machines and BLDCs. We choose three criteria to compare these motors: stator and rotor weight, torque density, and total cost. As we can see, the brushless DC motors and induction motors has much higher weight in comparison with switch reluctance. We will see the switch reluctance motor, and it doesn't have any copper in it or permanent magnets, so the weight is much less than these two motors. The BLDC motors has permanent magnet on the rotor, and induction motors has winding or a squirrel cage in the rotor. Brushless DC motors have higher torque density amongst these machines, and of course the total cost of brushless motors is much higher than two other categories. But still, switch reluctance motors has higher torque density, almost twice of induction motors. So in the applications that we need high torque density, like automations and aerospace applications, we can use SRM and BLDCs instead of induction machines. To choose between these two motors, we can pay attention to the price. Due to usage of permanent magnet as the most expensive part of these machines, BLDC machines have higher price in comparison with induction motor and switch reluctance motor. We can see the total cost of the induction machine and the switch reluctance machine are in the same range, but the torque density of switch reluctance machines are much higher than induction machines. Now let's see how these motors work. When we have excitation on the stator, the rotor always try to align the rotor pole to the stator pole to minimize the reluctance of the flux path. Here, imagine that these two coils have the current excitation. The rotor tries to minimize the reluctance of these paths. The rotor tries to rotate in the direction to minimize the reluctance of the flux paths here in the stator and in the rotor. The minimum reluctance will happen in the alignment of the rotor and stator. And this is when we have to disconnect the current of this phase and excite another phase of the stator to continue the rotation. This rotary magnetic field is generated by the power electronic circuits and switching drivers. Here is a sample of how switching drivers works. These are the windings of the stator, and due to the position of the rotor, we have to excite one of these windings. The excitation will happen by turning the switches on. When we turn the switch on, we will connect the DC voltage to the winding, and after we turn the switch off, the freewheel diodes will continue conducting until the current of the winding reach the zero cross. And this switching can happen for all the phases. The ideal waveform of the current in the phases are pure square wave. but due to the inductance of the windings, we can't reach this ideal shape. So we try to control the current with switching on and off this circuit. A sample of measured current in the phase is like this. We can't reach the ideal waveform, but due to the inductance of the winding, the real waveform of the current will be like this in each phase. And with changing the phase's excitation, the rotary magnetic field happens and the rotor continue its rotating. We can categorize the switch reluctance motors by number of phases to have a correct slot pole combination. As we use a segmented stator switch reluctance motor for this webinar sample, we will discuss about possible slot pole combination in these machines. NS as number of slots can be 2 km for an M-phase machine. So for a two-phase machine, we can have 8, 12, or n multiplies of these numbers for segmented SRMs stator. For a three-phase machine, we can have 12, 18, and multiples of it. And for a four-phase machine, we can have 16, 24, and multiples. The number of rotor poles should be integer, which is not divisible by m, number of phases. For this webinar, we choose 16 poles for stator and 14 poles for the rotor to simulate the segmented stator switch reluctance motor. Now let's have a look on modular stator or segmented stator switch reluctance machines. In conventional machines, we have lamination with a single part that contain all the stator teeth. But if we can design the stator as a segmented, we will lower the cost of stator manufacturing, because instead of production the whole lamination for the outer diameter of the stator, we just need to product a little piece of the stator, and it is modular. A single part can be produced and the whole machine will be created from much smaller piece. The other advantage of modular stator is maintenance. If we have failure in winding or lamination, we can easily replace the failure part without disassembling the other parts or the whole machine. And as we have segmented stator, we will have empty parts between the stator segments. So the material usage and the total cost of this machine will be lower than conventional ones. We have talked about the disadvantages of switch reluctance machine, and one of the most important ones was torque ripple and acoustic noises. To improve the characteristics of these machines, we can implement a permanent magnet in the stator flux path. With using a permanent magnet in the stator, when we don't have any excitation in the winding, the flux will close its path into the stator segment, because the reluctance of this path is much lower than the air gap path. But when we have excitation on the stator and the flux density in the segment of the stator increases and become higher, the flux of the magnet will go through the air gap and the rotor to close its path. In this way, the flux of the magnet will participate in the torque generation too. This little help of the flux of the permanent magnet will increase the average generated torque and lower down the torque ripple. In the simulation, we can easily see that when we don't have any excitation on the coils of the stator, the flux pass will happen all in the stator segments. And when we excite the coils, even the fluxes of the permanent magnets will go through the rotor and participate in the electromagnetic torque generation. Here is a sample of magnetic flux density distribution in the stator and the rotor when we don't have any excitation. We can see the stator has a little bit flux density without saturation, but the rotor is not part of the flux path of the magnets. So adding these permanent magnets in the stator won't create additional torque ripple or cogging torque in this machine. The switch reluctance machines doesn't have any cogging torque themselves without any excitation, but adding these permanent magnets will not add cogging torque to their characteristics because the rotor is not part of the flux path of these permanent magnets. To have a better insight, let's have a look at this rotating rotor when we have excitation on the stator. Here, this rotor teeth is going to align with the stator, and at this moment, the current of this phase is disconnected and the next stator tooth is excited. And the excitation of the next tooth will start right before the alignment between the rotor teeth and the stator teeth. As the most important output of the simulation, let's have a look on the electromagnetic torque with the machine with permanent magnet and without permanent magnet in the stator. The permanent magnets are placed between the stator teeth of the segments. So the blue diagram is the output torque of machine with permanent magnet, and the red one is the simple segmented switch reluctance machine. If we notice, we can see the red diagram has higher torque ripple as the distance between maximum and minimum value is higher than the PM assisted machine, and the average value of the torque is higher in the blue diagram too. So we increase the average torque and reduce the torque ripple with this enhancement. Now let's have a software demo and see how we simulated this machine. First, we will talk about the geometric design, and then we will have simulation type and setting of the simulation. Assigning materials, assigning coercivity of the magnets, and excitation is essential part of the simulation, and then we will analyze and see the results. Here is the environment of the software, EMWorks 2D. It is working on the base of SolidWorks as one of the best CAD drawing softwares. You can easily draw the geometry of the simulation and your electrical machines here in the SolidWorks, and then just add a EMWorks 2D simulation study. In the EMWorks 2D tab, we have to right click on the project and add a study to create electromagnetic simulation. In the study properties, we have different types of study. As we want to model the switch reluctance machines, we have to use transient magnetic, but we have other studies like AC magnetic, electrostatic, and magnetostatic simulations too. When we choose the transient magnetic, we have to define if we want to compute energy and compute circuit parameters or not, and choose the time duration and time steps of the simulation. We can check the box to calculate the core loss parameters too. We have other options like thermal coupling, translation motion, rotational motion, and coupling to the circuit too in this kind of simulation. In the advanced properties tab, we can choose how precise the meshing would be. If we choose 1 or 2 or 3, the size of mesh will change and affect the precision of the simulation and analyzing time. After we choose the transient simulation properties, we have to define material for each part. For example, we have coils here that are copper. So we will select each coil part, and by right clicking and apply material, we can choose the material from the default library of the software. We have conductor material, and we will choose the copper. Click on apply and close, and we will go to the other materials too. For example, when we have magnets, we have to choose the magnet parts and assign material as permanent magnet. We have different permanent magnets in the default libraries too. Here we have permanent magnet, we have all nickel, ceramic, neodymium, iron boron, and subbarium cobalt magnets here. The magnet we have chosen is N42 from the NDF-EB magnets. And we have to assign the stator and rotor as a hypermobility material. So we will choose them. Go to the material for the stator parts and the rotor part. We have to choose electrical steel material. We click on apply material, and in electrical steel we can choose different material with different standards names. After we applied all the materials to the simulation, we have to define coercivity for the magnets. Define the coercivity, first choose all the magnets, and as we mentioned in the slides, all the magnets are magnetized in the phi direction in the cylindrical coordinate system. All these magnets has this kind of flux density in the direction of the rotation, and all magnets have the same coercivity. So to set the coercivity, we can select all of the magnets, or if the magnets have different directions, we can select the magnets that we want to define that specific coercivity and right click on them, click on coercivity direction. In the options, we have to choose the coordinate system that we want to define and choose if they are in Cartesian or cylindrical direction. I chose the cylindrical, and in this cylindrical coordinate system I choose the magnets to be magnetized along the phi direction. All the magnets defined in the phi direction. We also need to put a vector potential on the edge of the simulation. I created a circle region and choose the magnetic vector potential as 0 on this edge. To calculate the force and torque, we have to choose the rotor and assign virtual work as compute force and torque on the rotor. We use the torque, but for asymmetric designs, maybe you need to compute the force too. The mesh can be default meshing of the machine, and the most important part is winding. We have 4 different phases, so we define 4 different stranded windings because the windings are stranded from different coils. And after we defined 4 windings, we have to choose the coils for each winding. We can select the coils, the positive and negative coils, and in the coils we can define the geometry and name and number of turns for each coil. The direction of the coil can be selected by current direction reverse or the positive side of this selection. So we define the coils and winding. To excite these windings, I choose the current excitation. We can double click on the winding to see the name and type of excitation. I choose the current driven coils, and in the current source we have many options like DC source, exponential, pulse current, sinusoidal, and other shapes, but I choose import current time curve and define different values for the excitation. We have to define the starting, stop, and the increment of the time stepping, and define the shape of each phase current. We have the 4 different phases, but the conduction time of each phase is a little more than 25% of the period to have better and more torque generation in the machine. Here is phase B, phase C, and the last one is phase D. You can see the phase A was here, phase B is here, phase C is here, and phase D is here. The simulation is complete, and we can analyze the simulation by click on the run, and after the simulation we can get many different diagrams and results from the result option. We can get the current density, magnetic vector potential, and to get the output torque we easily can click on 2D plot versus time, linear, choose the quantity as a torque, and add this parameter to the diagram. To have a better view, we can smooth the results and change the properties of the diagram plotting. In this diagram, we plotted the both simulation with magnet and without magnet in different times and excitation, in a single diagram to be able to compare the results. If you need more examples or more simulation on the software, you can easily find many demo simulation in EMWork products, EMWork 2D demo viewer. Many rotational machines and other geometries are available here as an example of the software. Now let's have a conclusion on this webinar. We saw that SRMs are good choices for many applications due to their lightweight, low production cost, and of course good force density, good torque density. Segmented SRM have lower production costs and total weight due to the empty area between the segments, and they have very good maintenance characteristics to increase the power density and decrease the torque ripple of these segmented SRMs. We use permanent magnets to increase the average torque and decrease the torque ripple. We simulated the geometry and the machine with the finite element software named EMWorks 2D, and the results are compared and shows the enhancement too. If you have any question, please feel free to type your question in the chat box, and my colleagues and I will answer all of them now. Thanks for joining today's webinar and have a good time.